Hello and welcome back. In this video, we're skipping to, technically this is in the appendix of the textbook, so A.3, but it is directly related to what we covered in our last video when we had an introduction to inequalities, and we were solving inequalities and giving their solution sets. So essentially this section will be about looking at the solution of multiple inequalities and combining them together. So that's where this compound part of the name is coming from. So imagine we have two inequalities. I'll just call it inequality A and then inequality B. So you'll be presented with two of them, and you'll either say that you want the solution to be in A and B, like the solution to inequality A and the solution to inequality B. This means that your solution needs to be in both of these at the same time. So in both at the same time. I want whatever my solution is, whatever my interval of x values, need to solve inequality A and inequality B simultaneously. We might also see questions using an or, so A or B. So meaning it can solve one of them, or it can solve the other, or both at the same time. So that one is a bit wider. So I can say can be in one or the other, or both. So we'll work through some examples and it'll become more clear what I mean by this. All right, so we're going to start with compound inequalities containing the word and. So first, let's just look at what one looks like, and then we'll take a look at these procedural steps. So looking ahead a bit at example 2, it's wanting us to solve the compound inequality c plus 5 is greater than or equal to 3, and 8c is less than or equal to 32. So previously we were just looking at one of these and solving, and then we get some kind of interval of solutions. And so this time we'll have two separate cases. We'll get two different intervals, and we'll need to determine, do we want to be in both of them at the same time? The alternative would be an or statement, where it could be in one or in the other or in both. So really this will end up being just solving two of these questions at once and then deciding how to merge their solution sets together. So let's look at their suggested steps for solving a compound inequality. So first they say to identify if the inequality is and or. So that'll come just in the question and understand what that means. Then the second step is just to solve each of them separately. Then it suggests to graph the solution set to each inequality on its own, like on its own number line. Even if the question doesn't ask you to, this will help you visualize the solution to the compound inequality. When you see each of them separately, we'll think about how to combine them together. And so this is where the procedure will split depending on if the question is and or. It says if it is an and inequality, the solution set consists of the regions on the separate number lines that would overlap or intersect if one number line was placed on top of each other. So it's only where they both exist at the same time, where they overlap. And we'll see some examples. If it's an or inequality, the solution set consists of the total of what would be shaded if you took the separate lines and put one on top of the other. And you can also call that a union. And so this is making a reference to some set theory um, terminology, a union or an intersection. So if it's and, you think about where they would overlap. If it's or, you just think about what would be the total amount that would be covered up if we were to combine the two solutions together. And then we use the graph to write the answer in interval notation. So let's go through a few examples. Let's return back to example 2. So we have c plus 5 is greater than or equal to 3, and 8 times c is less than or equal to 32. So let's solve each of these separately. On the first one, I'd subtract the 5 on both sides. So c will be greater than or equal to negative 2, 3 minus 5. And let's solve the other side. So we have 8 times c. Let's divide both sides by 8. We're dividing by a positive, so we don't need to flip the inequality. And then 32 divided by 8 is positive 4. So we have two solutions here, joined with this and. We could call that an intersection. So let's think about each of their graphs separately, as was suggested. So the first one, c is greater than or equal to negative 2. So if this is 0, negative 2 would be over here. I would include the negative 2 and shade in everything to the right of it. And then for our other solution, we have c less than or equal to positive 4. So less than or equal to, I'll include positive 4, and I want everything less than that. So on the left side. So since this is an and question, I'm going to imagine combining these two solutions together, but only include where they overlap. So on the left solution, it's from negative 2 onward to the right, and on the right solution, it's everything from the left up until positive 4. So this means we'll just have everything in between negative 2 and 4 as our solution. So only where they both agree on the answer. It's another way to look at it. So in my single number line, maybe I'll make this a little bigger. This would be 0, negative 2, positive 4. So everything greater than or equal to negative 2 and less than or equal to positive 4. So everything in between. It's kind of like those double inequalities where we had it as a single line on two sides. And we're just stating it as two different statements. So that would be the graph, and then in interval notation, we would write from negative 2, including negative 2, up until positive 4, including positive 4. Let's see another example. So this says, solve the compound inequality 7y plus 2 is greater than 37, and 5 minus 1/3 y is less than 6. So let's go through that process again. We'll solve the left side, look at the answer, solve the right side, look at the answer, and think about merging these together. So on the left, let's start out by subtracting 2 from both sides. So I'll get 7y is greater than 35. Then I have 7 times y, so let's divide both sides by 7, dividing by a positive, so I don't have to flip. So I'll get y on the left side is greater than And then 35 divided by 7 is positive 5. So this would be everything strictly greater than positive 5. So this time we would not include the 5, so I'll use parentheses and everything greater than that. Now let's look at this other one. We have 5 minus 1/3 y is less than 6. So we have a positive 5, so let's subtract it over. Then I'll get negative 1/3 y is less than positive 1. So we can see this as y divided by negative 3. So we can multiply both sides by negative 3 in order to cancel. And since we're multiplying by a negative, we'll need to flip the direction of the inequality. Remember, if we divide both sides by a negative or multiply both sides by a negative, we have to flip the direction. So since I'm multiplying this negative 3 over, I'll get positive y on the left side, and instead of less than, I will say is greater than. And then this would be negative 3 times 1, or just negative 3. So remember this rule because it's an easy thing to forget, and that can throw us off. So let's look at this solution. Everything strictly greater than negative 3. So greater, so everything to the right. And so let's keep in mind this is an and situation. We want the intersection of these two solution sets. So we have our two solution sets, and we need to think about where they intersect, where they overlap, where we would be inside of each of these at the same time. On the left side, it's everything greater than 5, but not including 5. And on the right, everything greater than 3, but not including 3. So if we were to put them on a single number line, we would need to see where they would intersect each other. And we can imagine, oops, positive 5 being somewhere up here. So the right one is from negative 3 onward, but this whole section up until 5 is not in this graph. So the only part where they start to intersect each other is from 5 and onward, but not including 5, because our answer on the left does not include the positive 5. So our combined solution would be, it would basically be what we have on the left there. Everything starting at 5, but not including 5 and onward. Because this portion going to the right does exist also in this graph, but only starting here and going forward. So that's where they would intersect each other. And then as interval notation, we would give starting at 5, going to infinity. So it might be a little bit tricky. We have to think about where they would overlap. All right, let's look at the next section. So we just looked at and questions. This will be an or question. So this says solve the compound inequality 6p plus 5 is less than or equal to negative 1, or p minus 3 is greater than or equal to 1. So let's continue that practice. Let's solve the left side. I'll subtract 5 from both sides. So I get 6p is less than or equal to, and I have -1 minus 5. Subtracting from a negative, it'll become more negative, -6. And then I have 6 times p, so I will divide both sides by 6. I'll just get p on the left side is less than or equal to -6 divided by 6 will be -1. And I'm dividing by a positive number, so I don't need to flip the direction. So this would be everything less than or equal to -1. So include the -1 and everything to the left of that. And then our second statement, we have p minus 3 is greater than or equal to +1. So let's add the 3 to both sides. So we'll get p is greater than or equal to +4. So let's think about that one. So 0, 1, 2, 3, 4. So everything greater than or equal to. So let's include the 4. This would be everything greater. So this is an or statement. If this was an and, we'd have to imagine where these two intersect and actually intersect nowhere. That would produce no solution. Since the left graph is everything from -1 to the left, this is from +4 to the right, they don't intersect anywhere. But since this is an or statement, we could have either one or the other. They can both, we have both of the options. They don't have to intersect, we just want to combine these two on a single number line. So an or statement is more forgiving. So let's just combine these together. This is 0, so -1 is here, 2, 3, 4 is over here. So everything less than or equal to -1, or everything greater than or equal to +4. So you can have these sort of like broken, discontinuous intervals. So let's write it as interval notation. We just want to say this one or this one. So the left interval is from -infinity up until -1, including -1. And then our second one is from +4 to +infinity, because it keeps going to the right. And we join this together with a union. That's why we used that term union earlier when describing an or statement. So we're just joining together these two separate intervals. We're saying either in this one or in this one. So that's an or. That one you just need to combine the two solution intervals together. Okay, let's look at our last section. So this is solving some special compound inequalities. There's a couple special cases that we'll run into. Let's look at these two and just try to solve and see what we notice. The first one says k minus 5 is less than -2, or 4k plus 9 is greater than 6. So let's just go as we would normally. We'll try to solve both of these. On the left side, I would add 5 to both sides. So k is less than +3. That's like 5 minus 2. Or on the right side, I would subtract 9 from both sides. So I get 4k is greater than 6 minus 9 is -3. So let's divide both sides by 4. And I'll get that k is greater than -3/4. So I get that k is greater than negative 3 over 4, or k is less than 3. So let's imagine them separately. This one says k is less than positive 3, 3, strictly less than. Or, on the right side, k is greater than negative 3/4. So if this is negative 1, 3/4 would be somewhere here. So everything greater than that. So this is an or inequality. So we would just imagine combining these two together. On the left hand, we have everything less than 3 off to negative infinity. So that goes forever. And then on the right side, we have everything from negative 3/4 off to positive infinity. So combining these together, we actually would just cover the whole number line. So let's look at it this way. If this is positive 3, this is negative 1. For my left inequality, I'm saying everything less than 3. And then on my right inequality, I'm saying everything greater than negative 3/4. So starting here and going off to the right, and it covers the whole number line. So this solution is all real numbers. In interval notation, we'd say from negative infinity to positive infinity. If you're using some kind of set notation, we would use the all real number symbol. So sometimes you might get the whole number line if you have an or statement. And then let's look at B. B says 1/2 W is greater than or equal to 3, and 1 minus W is greater than or equal to 0. On the left side, we have W being divided by 2, so let's multiply that 2 over. So we could say W is greater than or equal to 3 times 2, which is 6. And on the right side, let's subtract the 1. So we get negative W is greater than or equal to negative 1. And then when we divide by negative 1, we'll flip the inequality. So W is less than or equal to positive 1. And this is an and, so it needs to be both at the same time. So let's imagine already trying to think about where these would intersect each other. I'll just graph them both on the same number line. So we have, say this is 0, positive 1, 2, 3, 4, 5, 6, and positive 6 over here. So the left statement says everything greater than or equal to positive 6. The right statement says everything less than positive 1. So in this case, there's no intersection. If this was an or statement, like our left example, everything would be fine. We would just combine these two using a union. But remember, with an and, we have to give our solution as where whatever is in both of them at the same time, or where they intersect, or where they overlap. So since there's no intersection here, we would say no solution. And in the homework, you might use this symbol. So it means the empty set. There is no solution to this compound inequality. There's nothing we can plug in to W that will make both of these true at the same time. That's another way to look at this. So these are just some special cases. You might get everything as a solution, or you might get nothing as a solution. All right, so this was compound inequalities in one variable, and we were focusing on these and or statements. So again, and is an intersection of two solutions, and or is just a joining together, a union of two solutions. Alright, that's it for this video, and I'll see you next time.